on the solving equations on the proof page. So I may do these for the proof, and then I might start the third page in this video. So with that, let's just get started with solving. So sine of x over 2 equals the square root of 3 over 2. So the idea here is that I am going to end up speeding up my my clock here by a factor of times 2. So what's going to be beneficial is I just look in the first two quadrants between 0 and pi for what values will make the most sense to solve in this equation. So if I just think sine of what angles produce positive root 3 over 2, in fact, both are in those quadrants. That would be the pi over 3 and the 2 pi over 3 angle. So I get theta is pi over 3 and 2 pi over 3. But now to account for the fact that all these are going to get slowed down by a factor of 2, what I want to do is I want to double both of these values so that way I get the correct angles for when I substitute into the expression, and I can get that these two angles will be our solution here. Now, looking at number 11, cosine of 2x plus 7 sine x plus 3. Again, I don't want this and this to happen at the same time. So since this is the function that I can easily exchange, I'm going to use the identity 1 minus 2 sine squared x to replace the cosine of 2x equation. And now I'm going to do a little bit of rewriting here. Now, you may see it right here that I have a negative. So here's what I'm going to do. I'm going to move the entire equation over to the right-hand side so that way I change all the signs at the same time. So 2 sine squared x minus 7x. Sine of 7x. Negative 7 sine x. And then when I combine the 3 and the 1, this becomes a minus 4. So this problem is a lot easier to factor in that I get 2 sine of x plus 1 and sine of x minus 4. Oops, I already have the 0. So that means I want to know these two solutions. When does sine of x equal negative 1 and positive 4? Well, that's a problem because sine can never equal positive 4 by itself. So I really just have to answer the solution negative 1/2. And there's no double angle for sine in this case, so we actually don't have to worry about this. So I just need to now think about my unit circle, and the negative 1/2 angles occur at 7 pi over 6 and 11 pi over 6. So that's it. On to number 12. So here I can divide everything by 4. Sine squared of x plus pi over 6 equals 1/4. Take the square root. And so I get this solution. Sine of x plus pi over 6 equals plus or minus 1/2. Now, we just talked about what angles equal to negative 1/2, so that's 7 and 11 pi over 6. But since I also have the positive versions, I get the 1 pi, the 5 pi over 6, the 7 pi over 6, and the 11 pi over 6. And so I get that x plus pi over 6 equals all 4 of those solutions. So I get pi over 6, 7 pi over 6, oops, I forgot the 5. 5 pi over 6, 7 pi over 6, and then 11 pi over 6. And so when I go to solve this, I subtract by pi over 6 on all values. So this becomes 4 pi over 6, aka 2 pi over 3. This becomes 6 pi over 6, which is just pi. That one I will specifically reduce. And then this is 10 pi over 6 or 5 pi over 3. So those are my 4 solutions in this case. And then here, sine of 2x equals negative 2 cosine x. Again, because the angles are different, I really want to rewrite this in its one identity form. Here's a common mistake. Do not divide cosine. The reason why you can't divide by a trig function is like why we can't divide by variables, in that if we divide, there is a chance that the variable that we divided by becomes 0. In that case, we actually miss a possible solution. So what I'm going to do is I'm going to get everything on the same side so that it is factorable. We can see that there is a GCF of 2 cosine x. So I'm left with sine of x plus 1 equals 0. And so I have to solve this expression. 2 cosine x equals 0, sine of x plus 1 equals 0. And so I get when does cosine equal 0, as well as when does sine equal -1. And so both of those cases actually occur at pi over 2 for the cosine equals 0 and 3 pi over 2 for actually both of these solutions. So if you want to think of it like almost like a multiplicity in a sense, it is a multiplicity of 2, but we will not be writing it that way. And now on to the proof. So it is a column proof. This will not be a standard requirement on that test, but it is one that we've talked about. The first thing is that should be a minus if it's not already. So remember that when we do a 2-column proof, we're just kind of doing a verifying problem, but we are now writing it out as if it's a 2-column proof. So we start with a given. So we start with one on my side. So I've got tangent to the 4th omega plus tangent squared omega. And first I have a GCF of tangent squared. So I'm going to factor that out. And so this is where a lot of people like to kind of deviate. So I'm just going to use a GCF factor. Sometimes we can convert these things to sines and cosines, and that's pretty helpful. But just, as a way to kind of challenge the thinking here, this is not in terms of sine or cosine. This is just in terms of maybe a cosine function. So it may not be in our best interest to try to convert this into sines and cosines, then work out the cosines to reincorporate the cosines. What might be better is there another identity? And there really is. So we know that tan squared, this is one of our trig identities, or Pythagorean identities, is equal to 1 minus secant squared, which then tells us that secant squared is equal to tangent squared plus 1. So I'm going to actually do a double tangent Pythagorean substitution. So if I spell that right, Pythagorean identities, in that the tangent squared becomes secant squared omega minus 1, and the tangent squared plus 1 becomes just standard secant squared. And so now that we have that, we distribute, we get secant to the 4th omega minus secant squared omega. So I actually don't even need the 5th step. So we just distribute, and that's our proof. So we just use the fact that the trig identities, or the Pythagorean identities, are what I can swap both pieces with at the same time. So it's probably a lot easier than you might think. All right, on to the third page. So let's do 7, 8, 9, and then our last video we'll finish. So with this, we have a 2-angle tangent value here. So first thing is, let's construct our A angle. So this has to be in quadrant 1. It actually only restricts it in quadrant 1. So 4, 3, 5. And then I'm going to do B separately. So it has to be in quadrant 3. It doesn't give us another option. So that means that this is -12, this is -5, and then by Pythagorean theorem, that's 13. So to find sine of A plus B, what I'm going to do is I'm going to use the sine identity of angle addition. So that's sine of A times sine of B plus, that's sine of A cosine of B plus sine of B cosine of A. And so now that we actually have the triangles above us, we can actually substitute in the sine of A. So sine is opposite, so 4 over 5. Cosine's adjacent, -5 over 13. Sine of B would be opposite, -12 over 13. Cosine would now be 3 over 5. And so when I multiply, I get -20 over 65 minus 36 over 65. And I end up with -56 over 65. So once you build those two triangles, it's actually quite straightforward. Now tan of 2b, again, we have an identity for that. That's 2 tan b over 1 minus tan squared b. We already have this information, so that's actually really great that I actually don't even need the triangles for this. So I'm just going to replace tan of b with 12 over 5 and 1 minus 12 over 5 squared. So this is more annoying than anything else. You have to actually compute these two fractions. So I get 25 24 over 5 over 1 minus 144 over 25. This fraction in the denominator will become, 24 over 5. This fraction down here will become negative 119 over 25. Now, I've kind of used this trick with a lot of fractions. I'm going to multiply everything by 25. What's going to happen is this is going to cancel, and the 5 is going to reduce. So if I just multiply my 24 in my numerator, I end up with my final answer of 120 divided by negative 119 for an 8. Okay, and then finally tan of b over 2. So there's another identity in our sort of chart, which is 1 minus cosine of b over 1 plus cosine of b in a square root. Now with this, because it's tangent of b, it is in the positive quadrant for tangent. It's quadrant 3, so I don't have to make this square root a negative. Okay, so this is going to be a positive value. Now to do this, right, so we already know the b value, or the b triangle, so its cosine of b is negative 5 over 13. So we're going to replace cosine of b with that. So 1 minus negative 5 over 13 over 1 plus negative 5 over 13. And so my fraction up top becomes 28 over 13. Sorry, no, 8, just 8. Can't read my own handwriting. Becomes 18 over 13. There we go. Okay, and the denominator will become 8 over 13. So since the denominators are the same, we can cancel them. I'm left with the square root of 18 over 8, which reduces to the square root of 9 over 4, which ultimately becomes actually 3/2. So kind of an interesting answer there, I think. All right, so with that, now that we have that completed, you can go back, watch this video. In our last video, we'll do the last 4 problems on this paper. Okay, see you in the next one.